Hello, this is Mrs. Hedden. This is Chapter 14, Heat and Temperature, Notes 3. From the previous conceptual video, we talked about Carnot after watching those videos. And we said the Carnot cycle, the concept of how heat is circulated through an engine to do work, is really, really important. And that's what we're going to be eventually getting to. But to understand Carnot cycle, we must first understand how heat flows, which is what we're looking at this chapter. In other words, what does heat depend upon? And we've discovered that different materials contain different amounts of heat for the same mass. And we distinguish that by calling it a specific heat that is specific for that material. The next thing we're kind of looking at is how and why is heat transferred and what controls the rate of that transfer. And while we looked at it, we said there's no real way to determine how much heat an object has, just like we can't say how much work an object has. So we measure how much heat is transferred to and from an object, and that's called Q, the rate of transfer. Okay, and we did some work on it, some formulas and problem solving with Q. Okay, now we're going to go back and look at energy for a minute. Okay, an object contains energy in many forms. There's gravitational potential energy, which varies depending on the height, kinetic energy, which varies depending on the speed, and thermal energy, which is what we're looking at. And it varies depending on the average motion of the particles within the material. And we know temperature is directly proportional to it, but there's a lot to it that isn't just average motion. Okay? So to consider that thermal energy, another way of thinking about energy an object contains when we're talking about heat is the energy from the phase that it is in. Depending on the phase, the chemical bonds between atom molecules are either under a lot of stress, they're holding on really, really tight, or very little stress, they're holding on lightly. In a solid, the bonds are holding on very tightly. And when they do let go, it releases a lot of energy. It's like you have a spring and you've pushed it down really, really far, and you let go and it springs way up, hopefully not hitting you in the face. Bang! Lots of energy being released. In liquid, if to carry this analogy further, the spring is not being pushed down quite as hard. So when you let go, it releases some energy, boing, but not a lot. In a gas, you're not pushing on that spring very much at all. Going the other direction, to go from a gas to a liquid, you've got to really push down on the spring to get those bonds close together. You've got to put energy into the system. To go from a liquid to a solid, you got to push down even harder. So again, you're doing work on the system to push it in. So in this way, going from a gas to a liquid or a liquid to a solid, you're inputting work. So work is going into the thing. Input work. In this way, going from a gas to a liquid, going from a solid to a liquid or a liquid to a gas, boing, you're getting output of work. Work is coming out of the system. So I'm just going to try and do out work here. All right? And it's important that you keep remembering that, because that'll have an effect on whether energy is being released from the system or whether energy is going into the system, which has an effect on whether you put a negative sign in or a positive sign in, which has an effect on your problem solving. This amount of energy going into or out of the system depends on the number and strength of the bonds, which means number of molecules, which means basically the mass. Okay, and the force pairs, which is proportional to the type of molecules. So again, it's going to depend on the material. So heat that must be transferred to change a phase would be dependent upon the mass and the type of molecules. So kind of like a specific heat, we have another coefficient. This coefficient is the latent heat coefficient. Latent because we can't really see it well at all. And heat because we're still talking about thermal energy. We're adding work into the system using temperature and heat transfers, or Qs. So L sub F is the latent heat of fusion, F for fusion, And it's anything that involves going from a solid to a liquid phase or a liquid to a solid phase, hence the double-headed arrow. Either way, you use the latent heat of fusion. L sub V is the latent heat of vaporization, and again, it's anything going between a liquid or a gas. Again, a two-headed arrow, so it's going from liquid to gas or gas to liquid. Which way is going to be like a positive, negative direction? The term latent is used because the energy is hidden. It's potential energy you're either going to release or you must do work on the material to obtain. You do not see a change in temperature as you add or remove heat, only a change in the state of matter. Coefficients are kilojoules per kilogram or kilocalories per kilogram. Going to have to be a little careful with that kilojoules because you're going to have to worry about that 10 to the third. On odd occasions, you can go directly from a solid to a gas, which is called sublimation, or gas to a solid. And so you have L sub S, the heat of sublimation. Fusion, talking about solid liquids. Vaporization, liquids, gases. Sublimation, solid to a gas. There's some examples. I didn't find this helpful. And there's going to be problem-solving strategies, which we're going to get into some very complex two-step problems that are going to be interesting. We're going to go over that when we do the next video. We'll do some complex problems. The one for homework tonight, WebAssign number 3, is going to be fairly straightforward problems that won't be too complex. You're going to have a lot of problems in this section. And then after we get through these, we're going to go into ways heat moves, and those are going to be much easier. Thank you very much for your time.